Hello, my name is David Kurtz. In this video I will give a brief introduction to my master thesis. First, I introduce the background and motivation of my work. The field of web development is under constant change. In its most basic form, there exists a database storing all data relevant to a web service, a backend server which handles business logic like data management, authentication or authorization, and a front-end client which runs on end-user devices and allows users to interact with the web service. These components communicate with each other as seen in this illustration. Nowadays, it has become more common to provide more than a single client. Some companies provide different clients for web browsers, smartphones, smart TVs, and so on. Due to the amount of different involved components, a single web service can end up being developed by multiple teams and using multiple programming languages depending on the specific use case. An approach against big monolithic backend servers has emerged, where multiple smaller-scale microservices are used instead. Each microservice only handles a specific task, for example fetching the current price of an article in an online shop. However, this would increase the complexity of communication between the front-end and back-end. One way to solve this is a so-called microservice gateway, which provides a single API for the clients by forwarding and aggregating requests between all microservices. Now, this resembles a possible stack of a modern web service. The communication between components, demonstrated by the black arrows in this illustration, is handled by web APIs. Currently, the most used web API architecture is called REST. In a REST API, each resource has its own URL endpoint, using a uniform interface, and it utilizes common web protocols. However, REST itself is not a standard, which can lead to inconsistencies between different APIs. In contrast, GraphQL is a newer web API architecture. It only uses a single endpoint, but provides a more predictive interface through the use of a strongly typed schema and its own query language. A GraphQL schema can define numerous different kinds of types, including object types, which are similar to classes, interfaces, enumeration types, and more. A front-end client can then utilize the dynamic query language to request any amount of data, and the result will only include exactly what was requested. Another characteristic of the query language is nesting, which allows requesting directly related entities in a single call, as shown on these slides. The goal of my work was creating a microservice gateway and using the GraphQL schema in two ways: to provide a web API and to provide data modeling on which GraphQL servers and clients are generated from, therefore speeding up development time and decreasing errors and inconsistencies between the communication of the components. Following is a description of how this is achieved. First, the schema is passed into an abstract syntax tree, or AST for short. This is done using the official GraphQL library. However, to simplify the process of code generation, the official AST is modified into a custom model. Further information about these modifications can be found in my thesis. After this model transformation, it is used as input data for a template engine in combination with template files. The templates define the structure of the resulting source code. Multiple sets of template files have been developed for different use cases in programming languages. This way, GraphQL server and client code can be generated. In order to achieve this, all of the types defined in a GraphQL schema have to be converted to whichever language is targeted. However, some types can be converted independently on the use case, while the conversion is case-sensitive for others. The types depicted here are case-independent and can be reused for GraphQL servers as well as clients. Meanwhile, object types have to be handled differently. For the server side, two types are generated: a data type, which includes basic fields, and a resolver type, which handles more complex fields, like intertype relationships. For the client side, the generated code is additionally influenced by the specific query. In this example, these three types are generated. Notice how the lower two types are different even though they are based on the same object type from the schema. As such, the generated types are different between GraphQL servers and clients. This is a big difference to REST APIs, which use uniform interfaces that do not change between server and client implementations. All of the described steps are therefore used to provide a framework that can produce source code based on GraphQL documents and templates. Extensions are supported by providing template files that target several specific use cases and languages. This framework was then used to create a microservice gateway that uses generated source code based on a GraphQL schema and query documents. Thanks for watching this video.